In this video, we will learn how matrices can be used to solve systems of linear equations. Previously, we learned about the substitution and elimination method for solving systems of linear equations. And in this chapter, we're going to learn an additional method, which is translating the system of equations into matrices, and then doing something called Gaussian elimination to simplify that to where we can quickly find our solution. Now, before we begin solving these matrix equations, we first need to know how to translate systems of equations into corresponding matrices. And when you hear the word matrix, all a matrix is a collection of numbers and rows and columns that have a certain meaning. So for instance, if we are going to translate this system of equations, x plus 2y equals 3, 3x plus 5y equals 2, into a matrix, the way the matrix works is it organizes the two equations. So the first row is going to be for equation 1. The second row is going to be for equation 2. And then we have columns. The first column is for the first variable, in this case variable x. The second column is for the second variable, variable y. And the third column is going to be for the number that it's equal to. And then what we do is for the first equation, what goes in the first row, we write down in the first blank the coefficient in front of the x, which in this case, if we just have an x, that's an implied 1 times x, so we would write a 1 here. Continuing to figure out what goes in the first row, which is the first equation, but second column, which is the y value, you'd look at what's the coefficient in front of the y, which is a 2 in this case. And then in the same first row for the first equation, but the third column, we write what it's equal to. And in this case, that's a 3. And generally, to show that there's the equal to, we write a vertical bar in between them, so this shows the equal to. And then we have brackets starting and ending it, and we just continue that now with the second row, following the same ordering, except now it's working off of equation 2. So in the first entry goes the coefficient in front of the x, which is 3. The second entry is the coefficient for the y, which is 5. And the third entry is just what it's equal to, 2. And just like that, this is the system of equations represented as a matrix. And the nice thing about the matrix is, since there's so much in common with this idea of the x, we don't have to write 1x or 3x. It saves us a lot of writing. We just know 1 is the coefficient from the x, 2 is the coefficient from the y, add it together and you get the value 3. So it's a very efficient way to write these systems of equations. Keeping that in mind, let's write these as systems of equations as a matrix. We'll write the first one together since it involves 3 equations, and then I'll ask you to pause the video and attempt the next one on your own. Now, as we write this system of linear equations, as many equations that you have, that's going to be as many rows that you have in your matrix. So in this problem, since there's 3 equations, there's going to be 3 rows. And then you have as many columns as you have variables, 1, 2, 3, plus the equal to row. So there's going to be 4 columns, 1, 2, 3, 4. And we remember we work at 1 row at a time, so the coefficient from the first equation of the x is a 1. The coefficient from the first equation y is a 1 as well. Same for z, and then we do our equal to bar 9. And this tells us 1x plus 1y plus 1z equals 9. Next we have 6x, which is a 6, minus 4y plus 5z equals 31. 5x plus 2y plus 2z equals 14. Now take a moment to pause the video and rewrite this next system of equations as a matrix, as we did in our previous example, and then unpause to check your work. Now looking at this, since we've got 3 equations, we know we're going to have 3 rows, And there's 1, 2, 3, there's going to be 4 columns. The first equation has an x coefficient of 1, y coefficient of -2, z coefficient of 3 equal to 9. Second row has a x coefficient of -1, y coefficient of 3, z coefficient of -1, and then equal to -6, then a 2, -5, 5, and 17. And if it helps, always feel free to write x, y, z is kind of a key above that tells us that this column is the x coefficients, the y coefficients, and the z coefficients. Now, so far, all we've learned is how to translate. So we can now translate from a system of equations to a matrix, but we should also be able to do the reverse. We should be able to be given a matrix and write a system of equations. Remember, if you're doing that, then all the rows are one equation, and generally it's always x, y, and if there's another one before the equals, that's a z. So I could translate this first one to be 1 times x plus 2 times y, I get to my equals bar, equals 3. And then I would translate the next part of the equation, or the matrix, to be the equation 3 times x plus 5 times y equals 2. Now that we've learned how to represent a system of equations as a matrix, let's now see how this can help us solving systems of equations. So what I'm going to do first is I'm going to translate this to a matrix. Give everybody a minute to attempt this on your own. That would be 2 x's, 3 y's equals 6, 1x minus 1y equals 1/2, which I'm just going to write as 0.5. And as you're solving the systems of linear equations by matrices, keep in mind your goal. Your goal for a 2 by 2 matrix, so we've got a system of 2 equations and 2 variables, your goal is to get the matrix to look like this: 1, 0, 0, 1, and then some number here, and some other number here. I'm using different symbols so we can represent that. And what this would mean is that x equals whatever the number is there, and y equals whatever this is. So if we can get the matrix to look like this, 1, 0 on the top, 0, 1 on the bottom, then that's saying 1x plus 0y equals this number. That's the same thing as saying x equals that number. By reading the matrices, 0x's plus 1y equals this number. That's just saying y equals that number. So since these systems of these matrices are expressing systems of equations, that's why if we get this as our matrix, we're really solving the solution to get what is x and what is y. So this is our goal, but how do we get there? You can add and subtract rows of matrices, so long as if you're adding the matrices, you add everything in the first column together, plus everything in the second column, plus everything in the third column. You can also multiply by scalar multiples, so long as they're not 0. And you can move rows, but what you have to do is whenever you're moving rows, you've got to move it all at once. So for instance, I notice that the goal is to get a 1 in the upper left corner, but do we see there's already a 1 here in the bottom left of this example? So what I could do is I could take the entire second row and I can move it as the first row and just move the current first row down to second. And that's going to be part of the way to my goal because I'll now have that 1 as the upper left entry. Now as you're doing these matrix operations, it's important to write out what you're doing to help yourself stay focused, and then you can check your work. So here I'm going to say the current row 2 is going to equal the new row 1. The current row 1 is going to be the new row 2. And that's just telling me that I'm switching these. So the key thing is the whole row moves together. So all of this becomes the top 1, -1, equals bar 0.5, 2, 3, 6. Great. And then eventually we've got this taken care of, but we still need there to be a 0, and a 1. And the order that you seek to move these is important. After you get the 1 here, you start here, and then you get this. After you get this, then you get this. And after you get that, then you get that. And if we go out of this order, it's going to make it where we can't solve the equation because we'll keep undoing what we've done. So in this case, we're going to U-shape, get the upper left corner, then go down, then go to the right, then go back up. So our next goal is to somehow get this to be a 0. But you can't multiply by 0. That's the one thing you can't multiply by. So we're going to kind of do the elimination method here, except now it just looks like in a matrix. We're going to say if we want a 2 here, then we would need to add a -2 to this value. And we know with matrices I can add entire rows together. So I could take this row, and if I multiply it by -2, then I could add it to the second row, and I would get a -2 plus 2, and I'd get the 0 there. So that's going to be my goal, but to do that first I'm going to multiply everything by -2 in the top row, and I'm going to write that out as an explanation, and my goal is to get this 0 in the bottom row. So I'm going to say -2 times row 1 is my new row 1. Row 2 stays the same. So let's think, -2 times 1 is -2, -2 times -1 is +2, -2 times 0.5 is 1, sorry, -1. And it said just leave row 2 the same, we didn't do anything there. And now do we see we're in the position where if I add these two together and make that my new row 2, which you can do, you can add one row to another row to make it a new row. Then when I do so, these are going to cancel and give me the 0 that I was looking for here. So what I'm going to say is I'm going to say row 1 plus row 2 is new row 2. And we'll just write that out first, and then we'll discuss about what row 1 should be. So let's think. You have to go column by column. -2 plus 2 is 0. 2 plus 3 is 5. -1 plus 6 is 5. And then you ask yourself, if we put this back as our row 2, that defeats our purpose because we wanted the 1 here. The only reason we made this a -2 was to add it to row 2, which we've already done. So at this point, if you only change this to do something with it, then at that point, go back to the original. We were happy with this because it had the 1 in the right place. So at this point, I'm going to replace the original row 1 back in its place because I only multiplied it by -2 for a second so that I could add it to the second row, which I've already done. So I'm going to go back to the original I was happy with. 1, -1, 0.5. And we now check our list. We've now got the 0 below the 1. So next I move to get this to be a 1. So we look at it. It's currently a 5. Now remember, you can multiply by any number except 0. So 5 times 1/5 would make this a 1, and that would get me what I'm looking for here. So my next row operation is going to be, I want to take 1/5 and multiply that by row 2. And I would get 1/5 times everything in row 2. So 1/5 times 0 is 0. 1/5 times 5, well, we planned for this. That's going to be 1. That's the whole reason we're multiplying by 1/5. 1/5 times this 5 is also 1. And now we check, where are we at now? We've got this to be a 1. That's great. The last thing is that we want the upper right entry before the equals line to be a 0. Currently we have a -1. But here's the great trick. Since this is a 0 here, do you see if we took all of row 2 and added it to row 1, nicely the -1 and the 1 would cancel to give us a 0, which is what we're wanting. So that's what we'll do. We're going to say, we're going to take row 2 plus row 1, and that's the new row 1, and row 2 stays the same. So I'm going to leave row 2 as the same, just going to copy it down here. But now every column gets added together to be the new row 1, so 0 plus 1 is 1. That's why we want to make that 0 so it doesn't change anything. Negative 1 plus 1 is 0. 1.5 or 1 plus 0.5 is 1.5. And once we have the goal met, so we've got a 1, 0, 0, 1, then we can immediately conclude what are the values of x and y that are the solution to the system of equations. Well, from here it's saying, remember this is x column, this is y column, this is what it's equal to. So it's saying 1x plus 0y is 1.5, but that's the same thing as saying x equals 1.5. Here we've got 0x's plus 1y equals 1, but that's the same thing as just saying y equals 1. So here, through matrices, we've solved our system of equations. And as we're first getting started with this doesn't seem faster, but if you practice, it's a lot more efficient than solving even through the elimination method, particularly for larger and larger systems of equations. So in this case, our goal is to get it to look exactly like this, because once it looks like this, we can extrapolate our answers because it's literally isolated. This is what x is equal to, this is what y is equal to. We worked till we got that, and then we translated what our answer would be from there. Let's continue with our next example. Here we're going to solve the system of equation using matrices. Now our first step is to write this as a matrix. So I'm going to ask that you take a moment to pause the video, write this as a matrix, and then unpause to check your work, and we'll continue from there together. We know that each equation gets its own row, and then each column is based on the variable or what it's equal to. So the coefficient from the x for the first equation is 2, coefficient from the y is 1, it's equal to 11, coefficient from the second equation for the x is 1, and for the y is negative 3, it's equal to negative 1. And we always keep in mind our goal. For two equations and two variables, the goal is to look like this. Some number, some other number. They might be the same or different. And we know our goal is to go from the first upper left down to the right and then back up. So we're going to stay focused on the fact we want a 1 here. Now if there's already a 1 as the first entry on one of the rows, then the best thing is probably just to move that up to the front row, which we see this one already has a 1, it's just on the second row. So let's move that to the top row, and we're just going to write out our plan. We're going to say we're going to take row 1, maybe we could just write switch row 1 and row 2. That might be a quick way to write it. So the new row 1, all of it gets moved together as one unit. 1, negative 3, negative 1. Then we write the new row 2, 2, 1, 11. So we've taken what was first and made it second, what was second and made it first. And then we just mark down, okay, good, we've got this done. Next, my goal is to make this a 0. Currently it's a 2. Now remember, you can't multiply by 0, that's the one thing you can't multiply by. So if you're trying to make something a 0, generally that means that you've got to multiply the other thing by the opposite value so that when you add them you're going to get 0. So if we want to cancel 2, I need a negative 2, which means I need to multiply the entire first row by negative 2 so that I can then add that to the second row, because in matrices you can add rows together. So I'm going to write out that's my goal. I'm going to say next I'm going to take negative 2 times row 1. That's my new row 1, and I'm going to work in stages. I'm not going to add it yet. So negative 2 times each entry in row 1, so negative 2 times 1 is negative 2. Negative 2 times negative 3 is a positive 6. Lots of small calculations here. Make sure that you don't make any mental math errors. Negative 2 times negative 1 is a positive 2. And then we don't do anything else. We've multiplied negative 2 times all of row 1. I copy down row 2 as it is unchanged. And now we see that if I was to add row 1 to row 2, this would cancel and give me a 0 in the lower left corner. So we write out that intention. We're going to say row 2 plus row 1. That's going to be the new row 2. Let's write that out term by term. Negative 2 plus 2 is 0. 6 plus 1 is 7. 2 plus 11 is 13. And then, though this is the current row 1, we remember we only changed it in order to add, which we've already done. So at this point we revert back to our original row 1, which specifically had the 1 in the upper left corner like we wanted. So good, we've got a 0 there. We know our next goal is to get a 1 here. There's currently a 7, but I could get a 1 there by multiplying everything by 1/7. So in that case, if you can get there by multiplying, remember you have to multiply by a non-zero number, then do that. So I'm going to multiply row 2 by 1/7. So we'll write that out. (1/7) times row 2 is the new row 2. And that's going to be the row 1 is left unchanged. 0 times 1/7 is 0. 1/7 times 7 is 1. And then 1/7 by 13, I'm just going to call it 13/7 for now. And then looking at our goal, we see we've got the 1 there. So all that's left is to make this a 0. Now I know I can't multiply to get a 0, so instead I've got to manipulate the other row to turn it into the opposite value so that when I add them they'll cancel. So if I want to cancel a -3, I need a +3 here. So what times 1 gives me a +3? That would be +3. So next I'm going to say let's take +3 times row 2. That's the new row 2. Leave row 1 unchanged. And then 3 times 13 is 39 divided by 7. And now our goal will be to add the two rows together, because when we do so, this is going to cancel the first row second column and we'll get the 0 in its place like we were looking for. So we just write out of that instruction, let's take row 1 plus row 2, that's the new row 1, and after that we'll revert back to our original row 2. So we'll add these column by column. 1 plus 0 is 1. -3 plus 3 is 0. -1 plus 39/7, we'll have to calculate that off to the side. That's going to be equal to -7/7 plus 39/7. That would be 32/7. And at this point, we only changed this to add it. We've already done that, so let's go back to our original row 2, which met our goal more closely. And now that we've got the 1, 0, 0, 1, we have exactly x equals this, while y equals this. And that's the solution to our system of equations. Now this idea can be extended out to solve an equation in 3 variables. The only thing is now our matrix is going to have 3 rows, and our goal is going to look a little bit different. Whenever you're solving an equation in 3 variables, your goal is to eventually get 1, 0, 0, some number. Let's call it A, since there's going to be 3 of them. 0, 1, 0, let's say B. 0, 0, 1, which we'll call C. And once you get that, you know automatically that 1x plus 0y plus 0z equals A, which would give us x equals A. Similarly, 0x plus 1y plus 0z equals B. That gives us y equals B. And then we have 0x plus 0y plus 1z equals C, so we have z equals C. And that's how we get our solution. So this is our goal for 3 variables, and it starts off the same as before. We first need to translate this into a matrix. We know each row is this one equation, so if we've got x negative y plus z equals 8, that's 1x minus 1y plus 1z equals 8. Next equation goes to the second row. 2x's plus 3y's minus 1z equals negative 2. Next row, 3x's minus 2y's minus 9z's equals 9. And we have to keep track of our goal, and here the order matters as before. So first you go all the way down, and then what we do is we go over. Next we try to fix the next diagonal to be 1, and we go down. And then finally we go here and we go up. And then finally over. So our goal is to first fix this and then fix everything below it. After we fix that, we're then going to fix this one, fix everything below it. Next we're going to fix the next thing on the diagonal, but since there's nothing below it, after we fix that, we're going to fix everything above it. And then finally all that would be left is fixing this, which we'll fix at the very end. And then once we've got exactly this on the left, we can quickly decode our answers from what's left on the right. So let's always stay focused on our goal. We see that the first goal is to get a 1 in the upper right corner, which we already have, so that's already met. That just happened to be the case. Next, we know we want to get what's below it to be a 0. Now it's currently at 2, so you know that we can't multiply to get 0. We would have to change one of the rows, which is usually easier to change the row that starts with a 1 to the opposite value, so that when we add them they cancel. So if I multiply the top row by negative 2, everything else remains the same, so I've still got the same second and third rows. Then everything here by negative 2. Negative 2 times 1 is negative 2. Negative 2 times negative 1 is positive 2. Negative 2 times positive 1 is negative 2. Negative 2 times positive 8 is negative 16. Now keep in mind the goal of this is that we can then add row 1 and row 2 together, and the negative 2 and the 2 would cancel to give me that 0 there. So I'm now going to say row 1 plus row 2 is new row 2. So we'll add these term by term. Negative 2 plus 2 is 0. 2 plus 3 is 5. Negative 2 plus negative 1 is negative 3. Negative 12 plus negative 2 is negative 18. And then at this point, we don't write down the new row 1 because we only changed that to add, which we've already done. So we go back to the previous row 1 that we liked because it had the 1 in the upper right corner. Right row 3 is the same. So we keep track on where we are in our goals. We've now got the 0 there, so we just need the 0 below it. It's currently a positive 3, so think, what would I need to multiply row 1 by so that when I add them they cancel? Negative 3. So we're going to say negative 3 times row 1 is the new row 1. And we would take negative 3 times each term, so negative 3 times 1 is negative 3. Negative 3 times negative 1 is a positive 3. Negative 3 times positive 1 is a negative 3. Negative 3 times 8 is a negative 24. We write the other rows unchanged. And now our goal for doing this was so that we could add row 1 and row 3 together. So we'll write that down. Row 1 plus row 3 is the new row 3. So negative 3 plus 3 is 0. 3 plus negative 2 is positive 1. Negative 3 plus negative 9 is negative 12. Negative 24 plus 9, that would be negative 15. And then we rewrite the second one unchanged because it hasn't moved. And instead of rewriting that first one, we're going to go back to our original first one before we manipulated it to add. Back to this row. We keep track of our goal. We see we now have the first column done. So next I want to make the middle entry a 1 as well. Looking here, I currently see it's a 5. So I know I can multiply everything by 1/5 and that will turn that into a 1. So we'll say 1/5 times row 2 is the new row 2. Everything else is unchanged, so I'm just going to copy it out. So 0 times 1/5 is 0. 5 times 1/5 is 1. Negative 3 times 1/5 is negative 3/5. And then 1/5 times negative 18 is negative 18/5. Keeping track of our goal, we see that we now have this entry as a 1. That's good. So next we would do is we try to turn the thing below it into a 0. So we're going to make this a 0. And the thing is, we do not want to use row 1 anymore, because if you use any multiple times row 1, if you add it to row 3, do you see that would change our 0 from being 0? We want it to stay at 0. So at this point, we're only going to change row 3 by using row 2 because it also has a 0 in the first column. Whatever we do is not going to change the fact there's a 0 there if we only move with the second and third rows. So I have a 1 here, but I want a 0. That means I need to have the opposite value, negative 1, so that I can add them and get the 0. So that's going to be negative 1 times row 2 is new row 2. Everything else is unchanged. Negative 1 times 1 is negative 1. Negative 1 times negative 3/5 is positive 3/5. Negative 1 times negative 18/5 is positive 18/5. And our goal for this was to add it to the second goes to the third row, so that these would cancel and give us the 0. So now I'm going to say row 2 plus row 3 is new row 3. And we add term by term. 0 plus 0 is 0. Negative 1 plus 1 is 0. And now we'll need to do a little calculation off to the side to add 3/5 of negative 12. So we've got 3/5 plus negative 12. Well, negative 12 as a fifth is 3/5 minus 60 over 5, which is negative 57/5. So now we need to take 18/5 and subtract 15. So 18/5 minus 15, well, writing that as a fraction minus a fraction, that's 18/5 minus 15 as a fraction over 5 is 75 over 5. And then when we subtract those, that's going to give us a negative 57 over 5. Now let's copy this down on the next page, and we'll continue with our next goal is to get this to be a 1, following our pattern given here. We now have this as 0, so next is to make this a 1. Now we've been working on this problem for a while, but the timing is going to work a bit faster. Once you get what we'd call our main diagonal done, the remaining portions go a bit faster. Now this needs to be a 1. And what we can do is we can multiply it by its exact opposites, because we know negative 57 over 5 times what gives you 1? Well, the opposite would. So in this case, if we've got negative 57 divided by 5, we want negative times negative to give us positive, so negative 5 over 57. But the nice thing is whenever we multiply negative 5 over 57 times this, we get 1. But since we've got the exact same thing here, that's also 1. So I'm going to say negative 5 over 57 times row 3 is the new row 3. But what that's going to give me is 0 times anything is 0. So the first two columns stay 0. Negative 57 divided by 5 times negative 5 over 57. By the properties of reciprocals, that gives us 1, as does the second term there. And then our other rows that we haven't been working with remain unchanged. We make sure that we don't introduce any copying errors here. We check back with our goal. We now have this to be a 0 and this to be a 0, so next we need to turn this into a 0, and then this one, and then finally this one, and then we'll be able to see our answers just from what's it equal to on the other side. So here we're going to work to get this to be a 0. Now currently it's a negative 3/5. Remember, to get zeros, you can't multiply your way to 0. You've got to add another row times maybe some constant to that to make it 0. So what would cancel with 3/5 would be a positive 3/5. And you always, in this case, we don't want to multiply this one, because whatever we multiply it by, this 1 will change, and that will turn this from stop being a 0. Instead, we use the terms that already have zeros, because if we multiply this by something, this stays 0, and 0 plus 0 is 0. 0 plus 1 is 1. The only change is going to come from the last two terms. So we know negative 3/5 plus 3/5, that equals 0. So that tells me I need to multiply 3/5 times row 3, and that's going to be my new row 3. So 0 times 3/5 is 0, 0 times 3/5 is 0, 1 times 3/5 is 3/5, 1 times 3/5 is 3/5. Now next we're going to add row 2 plus row 3, and that's going to be the new row 2. Okay. So term by term, 0 plus 0 is 0. 1 plus 0 is 0. 3/5 plus negative 3/5 is 0. Negative 18/5 plus 3/5, since these have the same denominator, that is negative 15/5, which negative 15/5 is really negative 3. And the other rows remain the same, so row 1 is unchanged. And row 3, we're going to go back to the original row 3 before we had manipulated it to add. Checking back in with our goal, we now have this to be a 0. So the next thing is to get this to be a 0. Only 2 more things left. Now the only thing that can make this a 0, since this is a 0 in the second row, we've got to turn to the third row. Somehow we can multiply the third row by something and then add it to the first to get that to be a 0. The only way to cancel a 1 is to get a negative 1. So what we're going to do is we're going to take negative 1 times row 3 and that's going to be our new row 3 because we want to add it to row 1 later. Everything else remains unchanged. Zero times negative 1 is 0. 0 times negative 1 is 0. Negative 1 times 1 is negative 1. Negative 1 times 1 is negative 1. And now we're going to take row 3 plus row 1, and that's the new row 1. Term by term, 0 plus 1 is 1. 0 plus negative 1 is negative 1. Negative 1 plus 1 is 0. Negative 1 plus 7, plus 8 is 7. The other rows remain unchanged, and we go back to our original row 3. We're almost done. We've got the zeros above the 1. This is the last thing that needs to be changed. It needs to be changed to a 0. And then we think about it, which of the rows can help us? Because we want to get rid of this middle term. I would need to use a row that still has a middle term, which would be the second row. Because I can use this one to manipulate it in order to add, and that would cancel there. We wouldn't want to use the third row because the 0 is never going to help us get rid of that negative 1 in the first row. And in this case, they're already opposite values, so we can just add row 1 to row 2, and that will get us our new row 1, and we'll be finished with this problem. So we'll write that out. Row 1 plus row 2 is new row 2, new row 1. So 0 plus 1 is 1. Negative 1 plus 1 is 0. 0 plus 0 is 0. And then I just noticed one error that I need to correct here. Here I wrote negative 3, but then I wrote it as a positive 3 here, and here that's false. It should be a negative 3 from above, because negative 18 over 5 plus 3/5 should have given me a negative 15 over 5, which is a negative 3. So that was just a copying error that would have been problematic if it was not corrected. So now we add up the last entry, 7, and that should, be a minus 3 as well for the same reason as before. 7 plus minus 3 is positive 4. And then the remaining rows remain the same, so we've got a 0, 1, 0, negative 3, 0, 0, 1, 1. Now that we've met our goal where this is what the left side looks like, we can immediately read off our answers. X equals 4, y equals negative 3, z equals 1. And you could write your answer as like x equals 4, y equals negative 3, z equals 1. You might also see it as an ordered triple for negative 3, 1. Both of these are valid ways to write out your answer. So we've solved the system of equations in 3 variables. So going back to how this problem started, we found that for this system of equations, x was 4, y was negative 3, and z was positive 1. Why don't you take a moment to write this as a matrix? Pause the video and then unpause to check your work. So we'll translate this to a matrix. We get the first equation gives us a negative 1, negative 2, 1 equals negative 1. Second equation is 2 for the x, 3 for the y. We notice there's no z, so in that case the coefficient there is 0, equals negative 2. Now in the third equation there's no x, so the x term is 0. The y term is 1, and the z term is negative 2, equals 0. And we know our goal is to look like 1, 0, 0, 0, 1, 0, 0, 0, 1 equals some numbers. And if we can ever just switch rows to make this happen, we do so. So first, I noticed that this third row kind of looks like the second row, right? It's a 0 and then a 1. So I'm going to switch row 2 and row 3. think that would be helpful. Row 2 and row 3, switch. And that gets me a little closer to the goal. Row 1 stays the same. Remember, the whole row has to switch together. And then another goal at this point is eventually we're going to make this -1 into a +1. But do you see, before we change it out of the negative, I could multiply it by 2 and then add it to the third row, and that would get that to be a 0 as well. So we might as well take advantage of the negative sign while we have it before we change it. So I want to get this to be a 0, so I need to add a -2 to it. So I'm going to multiply this entire row by 2 and then add it to the third row. So 2 times -1 is -2. 2 times -2 is -4. 2 times 1 is +2. 2 times -1 is -2. The other rows remain the same. And now our whole goal was that we could take this and then add it to this and get the 0 like we wanted there. So I'm going to say row 1 plus row 3 equals new row 3. Term by term, -2 plus 2 is 0. -4 plus +3 is -1. 2 plus 0 is +2. And then we had -2 plus -2 is a -4. Second row remains the same. First row goes back to how it was before we did the scalar multiple. And now that we've cleared what's below the -1 here, let's turn this to be a +1 as we like. So I'm going to multiply the entire row by -1. Definitely recommend writing down these reminders to you so that we can describe what we're doing before we work through it. So -1 times -1 is +1. -1 times -2 is +2. -1 times 1 is -1. -1 times -1 is +1. The other rows remain the same. So far we've got this done. This, now we need to make this a 0. And we see that if I just add these as they are, they're going to cancel. So I'm going to say row 2 plus row 3 is new row 3. So we would take term by term. 0 plus 0 is 0. -1 plus 1 is 0. -2 plus 2 is 0. And then we get 0 plus -4 is -4. The other rows remain the same. And at this point, do we notice the entire row here is 0? That's going to raise big alarm bells for us in the future. If you ever have an entire row to the left of the equals line be 0, that means you're done with the problem. Because what this is saying is, as an equation, 0x plus 0y plus 0z equals -4. Well, what is 0x plus 0y plus 0z? That's the value 0. And is 0 equals -4 a real equation? Say, no, that's false, right? And what did we do last time we were solving systems of equations and we got a false statement? That meant that there was no solution. And that's the exact same thing here, except for systems of equations. What you're going to be looking for is if you get something where you get a false statement, which is a row of 3 or a row of all zeros, with it being equal to something that's not 0, that's when we know we have no solution. So I don't have to go any farther once I recognize that. So that would be our answer to this equation. There is no solution that fits the original systems of linear equations. So be sure as you work through these problems to stay focused on your goal, whether it's a 3 equation, it would look like this. If it's 2 equations, that's also 3. For a system of 2 equations, this is our goal. And then steadily work towards that with row operations. And then with any systems of equations, you can always check your answer by plugging in the values that you got into the original equations and seeing if they yield true statements. And finally, if during your calculations you ever get an entire row of zeros equal to something that's not 0, then your immediate conclusion is that there's no solution.